Okay, hi. Yeah, so I don't think many are going to join. Let us begin the session. All right.
Okay, sir.
Yeah. Okay. So in this session, we'll discuss week 8. Okay. We'll discuss the concepts of week 8. Okay. Within our time. So how many of you have gone through lectures of week 8? How many of you have gone through the lectures of week 8? You can raise your hand. Not 8, 2 lectures, 4 lectures, others. What about others? Have you gone through lectures of week 8?
No, sir.
None of you have gone through lecture of week 8?
I just started today.
Okay. What about others? Started. So only one person has completed. Okay. All right. Okay. Maybe but you still discuss the concepts of week 8. Okay. So for those of you who have watched the lectures, it would have been better if you watch the lectures, because we'll directly look at the slides. Okay. Slides of week 8, and then we'll discuss the concepts. Okay. All right. So let me share my screen. Are you able to see my screen?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay. So what do you mean by optimization? Can someone tell me? What is optimization? What do you mean by optimization?
Making it efficient so that, like, for example, when we create a model or, when we create a model, it does not differ that much from the original data set.
Okay.
Like, for example, if we take the dimensional reduction, in that case, so we get minimal reconstruction error or something like that. So that is an example.
Like more efficient way, sir.
Yeah, optimize to think anything to make the best use of the available resources, we can say.
Making it better.
Yeah. Yeah. Yes. Okay. So yeah, all of you are correct. Okay. So the optimization, right? So when we mean by optimization, we make the best of it, and then like we find the best possible solution. Okay. Like the best possible output which you wanna get, we have already got it. Okay. That means I mean that's what we mean by optimization, right? We got when we say that we got the optimized result or optimized value, we will be getting the best possible result, okay, or the output for a particular problem. Okay, that's what we mean by optimization. Okay, so the example was this dot, right? This green color dot. It was if I was a lecture, you would be knowing. Okay, this green color dot. Let's say it represents a cow, and then this blue color dot, it represents grass. Okay, so we should be knowing how close this cow can go close to this grass. Okay, the constraint is that the cow will be tied at this point, okay, by using a rope, right? But the she can extend that rope, and then she can go over the circle, okay, over the circle. But then the other content, other thing is that this is we have a wall over here, okay, we have a wall over here, okay, we have a wall over here, because so basically the cow cannot cross this wall, okay. So how close can it get? So basically we should be checking for all these points except for the points which were like crossing over, right? We should be checking the here when we mean like how close can it get. Basically we're trying to get the difference between the coordinates of the cow and the grass, right? Basically we just want to minimize that value, okay. Okay, I'll be sharing the I'll be zooming the slides a bit, okay. So the question is how close can a cow get the grass, right? So that's a problem, okay. So what is our what is our end goal? We want to minimize the x1 minus 40 whole square plus x2 minus 40 whole square, because that represents the distance between, let's say this grass portion is 40, 40, okay. Grass portion is 40, 40. So basically we want to minimize this x1 minus 40 whole square plus x2 minus 40 whole square, okay. The restriction is that what is the restriction here? See, this is the initial point of cow, right? So basically let this be 20, 20, okay, 20, 20. What does say? And then the length of the rope is, let's say, 5. Okay. The cow is out to 10 units rope, right? So basically, what is the first constraint is x1 minus 20 whole square plus x2 minus 30 whole square. Okay, it is at point 20, 30. Okay, x2 minus 30 whole square is less than or equal to 10 square, which is nothing but the constraint. I mean, the circle. Okay, the circle condition. Basically, this is only how far. I mean, the cow can only move to that much far, right? So x1 minus 20 whole square plus x2 minus 30 whole square less than or equal to 10 square. This is the first rope restriction. So basically, it can move within this within this blue colored region. Okay, within this blue colored region of circle. The other one is this fence restriction or the wall restriction, which was this one, right? Okay, x cannot be greater than 25. Okay, it should be only less than this. So the other restriction is this: x1 is less than or equal to 25. Okay, clear?
Yes, sir.
This is our optimization problem. Like basically, we want to minimize this. Okay, we want to basically minimize the distance from the cow to the grass. Okay, for doing it, these are optimized equation, but these are the constraints we got. I mean, these are the things which we need to obey, because in this particular case, since cow is tied to a rope, right? It cannot move greater than 10 units from the position where it tied. Okay, so that is why x1 minus 20 whole square plus x2 minus 30 whole square is less than or equal to 10 square. Okay, this is a circle equation. Okay, the any point inside the circle. Okay, and then the fence restriction is that we have this vertical fence. Okay, x1 equals 25. We have this vertical fence over there. So cow can only be on this side. Okay, it cannot be on the other side. So x1 is less than or equal to 25. These are the constraints. Okay, so we need to optimize this based on these constraints. Okay, so what do you want to do with the distance? We want it to be as small as possible, right? As small as possible. I mean, that is our end goal. Okay, so this is what we, I mean, for whatever we have written, right? The minimization of x minus 40 whole square plus x minus 40 whole square, that is called as the objective, because this is our main objective. We want to minimize the function f of x. In this particular case, f of x is I mean, it is a function of x1, x2, x1 minus 40 whole square plus x minus 40 whole square. Okay, let's say if you have like only one variable, okay, I mean we have this only one variable x. Okay, here in this particular case they are taking this d dimensions. Okay, just to generalize it. Okay, so in this particular case you can assume that d equals to 2 here, x1 x2. All right, so we need to minimize f of x, okay, over the variables of x belongs to Rd d dimensions. Okay, and then this is a objective function. Okay, this is called as objective function because that's our main objective. We want to minimize or maximize a particular thing. Okay, these are the conditions which we have. Okay, so we have this gi of x is less than or equals to 0, which is nothing but this inequality constraints, and then sometimes it could be equality constraints too. Okay, we can have this equality constraints. The equality constraints are represented by this h of x is equal to 0. In this previous case which we have looked at, x1 minus 20 whole square plus x2 minus 30 whole square is less than or equal to 10 square, and x1 is less than or equal to 25. Both these are inequality constraints. Okay, both these are examples of the inequality constraints. Okay, so I mean this is just a general way of looking at it. You take any optimization problem, you have this objective function, and then you could be having these constraints. Okay, sometimes you could be having unconstrained problem also. Okay, where there's no restriction, right? Let's say in this particular case, this cow is not tied to a rope. Okay, and then like there's no fence over here, which basically means it can move anywhere, right? So what is the least possible value of x1 minus 40 whole square plus x2 minus 40 whole square? What will be the minimum value of it? Can someone tell me? Hello?
0.
Yeah. So yes, so obviously the cow can go to the grass and then it can eat, right? So yes, that will be the minimum value. And then like let's say we don't have the fence. Then what will be the minimum possible value? It lies on the straight line. Actually, like if we just combine this, I mean this is a starting point, right? I mean this is the center of the circle, and then this is the grass. If you could make a line over here. The point where it touches the circle, from there you'll be getting this least possible distance. Okay, I mean the cow will be having the least possible distance from the grass. Okay, this is just a property of mathematics. Okay, nothing new there. Okay, you could even like check it by yourself. Okay, that is when we do not have a fence. I'm talking about the case of when we do not have fence. Okay, when we have fence, that becomes even more slightly complicated. Okay, so basically until now what we should be looking at is we'll be having something called as this objective function. Okay, we'll be having this objective function, and then we have this inequality constraints. Okay, for any given problem. All right, is this clear?
Yes, sir.
Okay, so when we have let's say like unconstrained optimization. Okay, let's say like we want to minimize this x minus 5 whole square. Okay, what do we do? I mean, how do you solve this directly?
Find the slope of differentiate it and equate it to 0. Basically finding maximum or minimum of it.
Right. So in our particular case, I want to minimize it, right? So I was having this x minus 5 whole square equals to f of x. Okay, so I'll differentiate it and then I'll equate it to 0. That's what you're saying, right? Right, f dash of x equals 0, and then
Yes,
it could be minimum or maximum. What is the condition for it to be minimum?
the second derivative should be above, like positive.
Yeah. So basically, f double dash of x should be greater than 0. When f dash of x equals 0 and f double dash of x is greater than 0, which basically means it will be having not it will have minimum value but local minimum value, not the global minimum value. Okay. So we'll talk about this in a bit. What do we mean by this local minimum and global minimum? Okay. So for example, let's say like we have this function of this of the equation of order 6. Okay, so we'll be doing this f dash of x equals to this. We'll be differentiating it and equal to 0. We'll be equating it to 0, and then we'll try to find the roots. Okay, all right, clear?
Yes, sir.
When you find the roots, there could be the points where you'll be getting local maxima also. So we do not want that. So basically what we do is we just check for this f double dash of x. Okay, all right. Until now, is it clear? Yes, yeah.
Can you go through the previous slide?
Yeah.
Yes. Is it always mandatory to have these two conditions? Can you scroll bit a little? Yes. The constraint
This
part. Yeah. So is it always mandatory to have all these two constraint?
inequality constraints and equality constraints?
Yes. Yes.
No,
Suppose we have a functions and there is only one constraint, like inequality constraint. Then
yeah, that's totally okay. See, this is just a general form. Okay, this is a generic form of like optimization problem. Okay, you need not have this constraints at all also. So in this particular case, right, unconstrained optimization, what we're doing, we're just trying to minimize the x minus 5 whole square equal x minus 5 whole square, right? Okay, so what do we get here? At x equals to 5, at x equals 5, we'll be able to minimize it. Okay,
yeah.
right?
Yes, I understood, but I'm talking about the general case. Suppose we have some functions and its constraints lie between some range. So is it possible to that its inequality constraint will lies in some limit? I mean,
You're talking about equality constraint.
yes, yes, yes. It will
Inequality constraint. That's what you're trying to say.
inequality constraint. Will it lies in some limit? I mean, between some value. Suppose gix is smaller than 0, na?
Yeah, yeah.
So is it possible that it will lie some fixed value, suppose -5 to 10 and something?
When you're talking about GFX is less than or equal 0, right? It
Yes.
doesn't take a single point, right? It takes multiple points there.
No, sir, I'm not talking about this. I'm talking that whether gix
Yeah.
will it lie in some range or not. I mean, suppose gx lies between -5 to 10. It is
Okay,
greater
okay,
than
okay. So
-5.
you're talking about the function GFX.
Yes,
Is
yes,
that it?
yes.
It depends on that particular function, right?
Mhm.
It depends on that particular function. Let's say like we have this GFX is let's say x minus 5 whole square. Okay, let's take this GFX itself as x minus 5 whole square. Okay, and then our condition is x minus 5 whole square is less than 0. Will it be ever possible? No, right? No, right? So the range for x minus 5 whole square is it will be 0 to infinity. If you're talking about a range for the function x minus 5 whole square, that let's take this g of x as x minus 5 whole square. Okay, so the range for that particular function is 0 to infinity. But let's say in some other functions that need not be the case, right? Okay, so the range for g of x it completely depends on that particular function.
Okay.
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 And then based on that based on that particular function range. Okay, and then the inequality that was given to us, we will be able to look at all the possible values. Okay, I mean all the possible values of x. Okay, within which we'll try to optimize it. Okay, is this clear? What I was
Okay.
trying to
Yes.
say?
Yes.
Like for example, if we have this x minus 20 whole square plus x2 minus 30 whole square is less than or equal to 10 square. All these points inside the circle, they satisfy this criteria, right? Within using these points, we want to get that particular value of x1 comma x2 where this x1 minus 40 whole square plus x2 minus 40 whole square will be the minimum ever possible. Okay. Is this clear?
Okay, sir.
Yeah.
Yes.
Okay. So let us move on to the second one. Okay. So let's say, right, we want to get this. We want to get this optimized value, right? Okay, like or the x value at which we'll be able to we'll be getting this optimized value. Okay, where f of x will be the optimum. Okay, so how do we get this parameter xt? Okay, so let's say we will be starting. I mean, there is a direct way of doing it that is using this f dash of x. Okay, the derivative, using the derivative you'll be able to do it, but then in most of the cases or then in higher orders, okay, doing the derivative, it's not so possible. Okay, it's not possible. Okay, so for that what do? We use this iterator approach. In the iterator approach, what do? We just assume initially some particular x naught as an x naught as an initial value. Okay, from there onwards you try to move, and every iteration you try to move close to the optimized value. Okay, we, like, for example, let's say we want to minimize this x minus 5 whole square, right? We want to minimize this x minus 5 whole square. So I'll be starting at somewhere at 8. So what I want to do is I want to move closely. I want to move in the direction of this optimized value. We know that since this is x minus 5 whole square, okay, we'll be getting the minimum value which is 0 at x equals to 5. Okay, the minimum value for this objective function is 0, and that occurs at x equals 5. So basically from x not equals to 8, if that is a initialization value, we want to move close to this optimized value, right? We want to move in the direction of in the direction of 5. Okay, so if you are at x not equals to 8, we need to move to the left. Okay, suppose let's say like we started with 1, right? We need to move to the right. So that we'll be able to, I mean, we will be moving in the direction of the optimized value. Okay, is this clear what I'm talking about?
Yes, sir. Yes, sir.
Okay, so this let's say like we were at this xt, right? For the next iteration, what should be this xt plus 1? I mean, what should be the next iteration x value? The next iteration x value, which is nothing but this xt plus 1, is given by xt plus d. Okay, the d is the distance which we should be moving. Okay, I mean, you can consider kind of like direction also. Okay, so the direction, right? How do we get the direction? Okay, how do we get the direction? So, for example, when we have this x is greater than 5, then we want this d to be less than 0. Okay, we want this d to be less than 0 because we know that we know that our optimized value is x equals 5. But only when d is less than 0, we will move in the direction of optimized value. And then when x is less than 5, we want to have this d is greater than 0. Okay, so if we take this minus f dash of x, okay, if we take this minus f dash of x, what's going to happen is when x is greater than 5, you'll be getting this minus f dash of x is less than 0. Okay, which we want, we'll be getting this d is less than 0. And then when x is less than 5, you'll be getting this minus f dash of x is greater than 0, which we want for the case of for the case of d is greater than, I mean, for the case of x is less than 5, we want this d is greater than 0. So if we're taking this d as minus f dash of x, right, you'll be getting greater than 0. Okay, so in either cases, we want this, we can choose this d as minus f dash of x. Okay, because by taking this minus f dash of x, we were able to move in the direction of optimized value. Okay, is this clear until now? Why exactly minus f dash of x? We'll discuss that in a while. Okay, is this clear until now? At least the idea, is that clear?
Yes, sir. Yes.
All right. So now we know that we need to move in the direction, right? I mean, if you move in the direction of minus f dash of x, then that's a good direction, because we are basically moving towards a direction where there is optimized value, okay, where there is optimized solution. Okay, for example, if you take this x not equals to 10, okay, if you take this x not equals to 10, what's happening here is, okay, you will be having this d equals to minus f dash of x like we are did. Okay, since f of x is x minus 4 whole square, f dash of x is going to be equal to 2 into x minus 5. Okay, minus f dash of x is going to be minus 2 into x naught minus 5. If you substitute x naught as 10, you'll be getting this d value as minus 10. Okay, you'll be getting this you'll be getting this d value as minus 10. Okay, which basically gives the x1 as x naught plus d 10 minus 10, which is going to be 0. Okay, you'll be coming across here. Okay, now we have this x1. Okay, initially we assumed x naught as 10 using this using this good direction methods, that is using this d equals to minus f dash x. We were able to move for second iteration to x equals 0. Okay, that is x1 equals 0. Okay, and then in the third iteration, right? In the third iteration, so we want to get this x2 equals to x1 plus t. We'll be repeating the same form, same method, but here x1 equals 0 now. Okay, x1 equals 0 now. So what do we get? F dash of x to be equals to minus 2 into 0 minus 5. Okay, minus f is going to be minus 2 into 0 minus 5, which is going to be 10 now. It won't be 0 now. It won't be minus 10, but it will be 10. Okay? Which gives us x2 as 0 plus 10, which is going to be this value again. Okay, which is going to be this value again. Now we could see it when we have this, when we have x equals to 10, right? When we have x equals to 10, you're coming to 0, and then it is again in the later iteration, it is again going to 10. Okay, and then you could see that if you use the same formula, after this when you get this x2 as 10, you'll be again getting x3 as 0. You'll be after that you'll be getting x4 as 10, x5 as 0, x6 as 10, x7 as 0. This thing is going to repeat itself infinitely. So basically you'll be just oscillating in between. Okay, you'll be moving in the right direction, but you won't exactly be reaching this optimized value of 5. Okay, it's kind of like you'll just be, it's like you'll be oscillating in between a pendulum, and then like you'll never stop. Okay, you'll never stop. It'll just oscillate with this optimized value center, but then it'll never stop to reach this optimized value. Is this clear what I was trying to talking about? Hello, is this clear?
Yes.
Okay, so until now, like we have established that we need to move in the right direction, but then the other important thing is it's not just the direction that matters, but the amount that you move, that also matters. Okay, if you're moving the amount as minus f dash of x, then that does not work in some cases. Okay, so we should be changing that. Okay, we'll discuss about that now. Okay, so now what we have is, we know that we should not be having it as like minus f dash of x. So what we introduce is, we'll be introducing a step size. Okay, we'll be introducing a step size. So the idea behind that is, let's say initially we will move to x1, and then like after that, using the step size, we won't exactly reach to x0. We'll be reaching somewhere in between. Okay, the step size reduces its overall value. Like initially step size we want that to be less than 1. Okay, less than or equals to 1. Okay, if you have taken this eta t as 1, that is just the previous problem, previous scenario. Okay, where we are not exactly getting this getting the optimized value. We are like oscillating in between, but we are not exactly getting it. Okay, for you to actually get it, Okay, the idea behind is you want to have the steps such that after some n iteration, it will be able to reach reach the optimized value approximately. Okay, so one way one way of choosing the steps is as 1/2 power t. Okay, so basically when we have this eta naught for the first iteration, we'll be having this eta naught as 1 because t equals 0, and then for second iteration we have this 1/2. After that we have 1/2 square, 1/2 cube, which is nothing but 1/8, and so on. Okay, but the problem with this is we might be reducing our step size so much such that we'll be kind of like initially we have this eta naught equals to 1, right? Okay, we are moving in the right direction, but then we might not even end up at the optimized value, even if you are done, let's say, so many number of iterations. Okay, even after you are done like infinite number of iterations, because you're reducing your step size so much. Okay, let's say after n number of iterations, right? Let's say if n is like greater than 10 or something, 1/2 power 10 value by 1/2 power 10, you're reducing this f dash of x, right? Restrict how far you can move. Okay, how far you can move. We should be restricting it, but in this particular scenario, we are restricting it too much. Okay, so that is why if we start at 2, suppose if you have this optimized value at let's say 5. Okay, let's say 5. We might not even like end up at 5. We might after so many other iterations, the maximum value it could reach only 4. Okay, only 4. Am I making sense now? Here? Hello.
Yes, sir.
Okay. Yeah. So we might not like no matter how many other iterations we do, we will not be getting close to this optimal value. So that is why 1/2 power t, right? That is not a good step size to choose. Okay. So the other one is this. We can choose the step size as this 1/t+1. Okay, 1/t + 1. So the sum of the step sizes, it will be infinity. Okay, it will be infinity. The key takeaway is that since the sum of step size is infinity, right? We could still be reaching this. We could still be reaching the optimal value after some finite number of iterations. Okay, since for this particular scenario 1/2 power t, right, the sum of step sizes, it's going to be equal to 2. Okay, like this is just a geometric progression. Okay, where r is less than 1. Okay, so the sum of the infinite number of terms is a by 1 minus r, which is going to be equal to 2. If you just substitute a equals to 1 and then r equals to half, you'll get this value as 2. Okay, the sum of the steps is only equal to 2. So that is why we are not able to get. We might not be able to reach the optimal value if you are taking the step sizes. But if you are taking this 1/t+1, then since the overall sum of the steps, right, that is 1/t+1, that's going to be infinite. Okay, you'll still be able to reach the optimal value. Okay, you won't be oscillating like you were before. You'll be getting the, you'll be able to reach the optimal value after some finite number of iterations. All right, clear? So now we have this formula for this. Like we have this xt+1 equals to xt minus eta t f dash of x, right? So this eta t, it's going to be equal to 1/t+1. Okay, all right. If you take this eta t as 1/t+1, then that is this gradient descent algorithm. Okay.
Can't we just have eta t as some constant?
If we have this, the eta t, right, as we move on, let's say, as we move on, the movement should be restricted.
Yeah, it's reducing it here, but what I'm thinking, if you have something like 0.1 or something, slowly it will converge, right? no worries of other things. That's what I thought. Maybe I'm wrong.
Slowly it's going to converge. Slowly it's going to converge, is it? That's what you're trying to say?
Yeah, I mean, here it'll definitely happen, but as we process, as we go further here, what I'm seeing is that eta t value gets reduced. It becomes smaller, smaller, smaller. So whatever the thing you should happen. So what initially the problem was with 1 by 2 power t is it becomes very small, that eta t value. So it doesn't converge at all. That's what you told, right? So I was thinking instead of eta t, if we have some constant, maybe 0.1, 0.2, will it work?
The idea is that we need to be we need to be choosing eta t as a function of t. Okay, it should not be taken as a constant, because as we move on, right? As we move on, we need to be getting it like very close to this very close to this
It should
close to the
reduce
actual
eventually.
optimized value. Okay, as we move on, we should be reducing. I mean, we should be restricting this f dash of x moment. If you take this
Got it.
point one, right, you like it doesn't matter whether it is a first iteration or let's say the 100th iteration. Okay, you'll be reducing it by a constant value. We do not want that. That is why we use this step size as a function of t. Okay.
Okay. Thank you.
Okay. So if you take this eta t as 1 by t plus 1, that's a formula for this gradient descent. I mean, that is just a general that is just the algorithm we use for this gradient descent. Okay, right. So I was talking about this eta t as 1 by t plus 1. The algorithm converges, right? Okay, the algorithm converges, right? What do you mean by converge? Right? When will it converge? We have this. We have this. Let's see. Okay, we have this d equals to minus f dash of x, right? Minus f dash of x, right? When we mean by converge, what does it mean? We won't be able to move further, right? That's our optimal value. When we will not be able to move further,
When it is at the lowest point, and the slope is 0.
hello. If you're yeah, so how do you explain it in terms of this xt plus 1 and xt? Can someone tell me? When xt plus 1, okay, I'll tell you. Okay, when xt plus 1 equals to xt, then that means that we are not moving further. Like we have error at the solution, right? Am I correct?
Yeah.
When xt plus 1 equals to xt, then that basically means we have reached the optimal value. We have reached the solution. Okay. When does that happen? The d should be 0, right? Because xt plus 1 equals to xt plus d, where d is minus f dash of x. Okay, when xt plus 1 equals xt, which basically means d is 0. When d is 0, what does that say? Minus f dash of x is 0, which basically means f dash of x is 0. Okay, right? Clear? The algorithm converges. The algorithm converges at local minimum, and then the local minima is a point where you have this f dash of x is less than is equal 0. Okay, f dash of x is equal 0. Okay, the point the definition for the local minima is, let's say within the small range, we have this blue color point here, right? We have this blue color point, right? Point here, right? Within the small delta, that is like plus or minus, let's say this particular value is 5. Okay, let's say this particular value is 5, and then like 5 plus or minus delta within the values of 5 plus or minus delta, right? F of x plus or minus delta should always be less than or equals to f of 5. Okay, which basically means within that small range, within that small range, this f of x is the least possible value you could get. Okay, then we'll say that, then we'll be saying that hello, hello, can you hear me? Hello.
Yeah, we can hear you now.
Okay. You have lost me. Where did you lose me? I was discussing about this. Minimum value.
Yes, sir.
Okay. Yeah. So what do you mean by local minimum? Within a small range, let's say this is x equals to 5. So for us to say that x at x equals to 5 will minimum value.
So there is it's getting disconnected a bit. I'm not sure if it is my network issue or it's happening for everyone.
Okay. Can you guys hear me properly now? Hello, can you
Yes,
guys
I
hear
mean,
me?
for a while I can hear, but later it's getting disconnected. So I'm not sure if it is just for me or is it for everyone else.
Yeah, actually, the problem is from my end. There is this, the network is not stable here. Okay.
Okay.
Yeah. So I'll try to repeat this again. So what do you mean by local minima is within the small range, within the small range of this x, let's say x equals to 5, and then the delta is small. Within small range of delta, that is within a range of 5 plus or minus delta f of x plus or minus delta will always be less than or equals to f of x. Okay. I mean, if you take this x as 5, f of 5 plus or minus delta should always be less than or equal to f of 5. Which basically which we're trying to say is you either move to the right or you move to the left. The only least value you could get is at this x only. Okay. All right. So that is what we mean by the local minima. Okay. I'm not talking about the global minima. I'm just talking about local minima. Okay. The local minima is, I mean, the global minimum is you take a extra where you'll be having this global minimum. Okay, f of x star is always less than or equals to f of x. Doesn't matter what the value of x is. Okay, x could be whatever range. I mean whatever domain this functions depend on. Okay, this is clear. In this particular example, right? We have this blue colored points, all this blue colored, even this red color point is also local minimum, but then this red color point alone is a global minimum, but others are not global minimum. Okay, but all these blue colored points, they are local minimum. Okay, this is clear. Even sir has not highlighted it, but then here also we have a local minimum, and then here also we have a local minimum. Okay, this is clear.
Yes.
Okay. So when we are saying that by gradient descent algorithm it converges, right? What do we mean by it? Let's say I took a point here. Okay, I started at a point here. Okay, I mean initially I need to be choosing some arbitrary x value, right? Let's say I took this as x naught. What's going to happen? It's going to converge to this point. It's going to converge to this blue Hello, can you hear me? Hello.
Yes, you're audible now.
Okay. Okay. So give me a second. So I need to be made co-host. So while I was, it's going to take some time, I guess. Before I'll be made co-host. So like how long? How is it until now? Until the week 7 of MLF, is it fine? Are you able to understand the concepts well? Are you able to process it?
So week 7, there are a lot of doubts regarding how to solve. Like concepts are clear because in practice problems, questions are solved in a different way than it has been described in the lecture.
Okay, so week 7, right? So okay. Yeah, we'll try to have separate session for that again. And then like moreover before this, right? We are going to have a revision session. So for that we'll try to solve this out. Okay. Yeah. Apart from this, so apart from week 7, and then like okay, is it even in week 7 also, is there like any other problems you're facing?
Sir, for me, I think for me, rather than a different session, just if you could solve one problem, that would be enough. That would give us a lot of clarity.
Okay, so it's just the problem solving that you're facing difficulty, right?
Yes, sir. Just one problem, if you could solve, that would give us clarity on how to solve the problem.
Okay. Yeah, we'll try to do it.
Thank you.
So just give me a minute. I'll just contact the studio team to make me co-host. Okay, so just a moment, I contacted them. Okay, so I'll be made co-host and then we'll resume session again. Okay. Yeah, sorry for the delay. Okay. Yeah, so let me share my screen. Okay, so we were talking about this global minimum, right? So let's say we started at this point. I mean, this is the arbitrary point we chose for the gradient descent algorithm. Okay, we will only end up here at this point. Okay, we will end up at this point because at this point only because that is a global minimum. Ideally for this particular function, right? For this particular function, this should be the global minimum. This should be the optimized x value. Okay, but then our gradient descent algorithm, it doesn't help us to reach at this point. Okay, it will only help us to reach us at this point because we have chosen this as the because this is the point which we have chosen as a starting point. Okay, if we had chosen within this vicinity, right? Like, are you able to see my mouse pointer? Are you able to see my mouse pointer? Students, are you able to see my mouse pointer?
Yes, sir.
Okay, yeah. So if you are chosen within the vicinity of this red color point, right? That is the global minima. Then our gradient descent algorithm gives us the global maxima. Sorry, global minima too. But then we do not know that, right? We will not be knowing that. We will not be knowing that we should be choosing the arbitrary point within this range of this extra. How do you know it? We do not know it, right? So basically this gradient descent algorithm, it is not a very good algorithm when you do not have this local minima equals to global minima. Okay, that is, let's say there exists a function f such that all the local minimas are global minimas, which basically means wherever this all these points, that is all these blue color points, right, they should be having same f of x value. Okay, they have same f of x value. That is that is all the local minima or the global minima itself. Okay, then we could say that it doesn't matter. It doesn't matter from which you choose as the arbitrary starting point. You'll be getting the optimized solution using the gradient descent algorithm. Okay, is this clear? Okay, is this clear?
Yes, sir.
Minima should be the global minima. Okay, so if that is the case, if all the local minima are the global minima, then those functions, those type of functions are called as convex functions. Okay, so for those particular functions, right, for those particular functions, we can use the gradient descent algorithm. Okay, for the other particular functions, right, you can still use the gradient descent algorithm. Okay, but then you won't be getting the optimized solution. All right, I hope this is clear, because in this particular example, in this particular f of x, this is the optimal solution. This x star, right? This red colored point, that is the optimal solution. Using gradient descent algorithm, you could end up at any point. You could end up at either this blue colored points, or you could end up at this red color point. You never know. Okay. It all depends upon the arbitrary starting point which you choose. Okay.
Yes, sir.
Yeah. So now I just told you guys that we will be choosing this. We'll be choosing this d as is minus f dash of x, right? What is so special about it? Okay, what's so special about it? So for that, let us look at the Taylor series, right? Do you guys know this Taylor series expansion? Have you guys ever looked at it? F of x plus eta d equals to f of x plus eta d f dash of x plus eta d square f double dash of x plus and so on. Have you looked at it? Yes, no? Hello. This Taylor series expansion, this Taylor series formula, have you looked at it before?
Yes, sir.
Okay. Yeah. Even if you haven't looked at it, just remember this, that let's say you know the entire information at a particular point. Okay. Let's say this is a point X. Okay. This is a point X. At this particular point, you know the entire information. That is f of X. You know this f dash f X. F double dash f X. You know f triple dash f X. F differentiated 4 times, 5 times, like whatever information you need at this particular point, you know it. Okay. So how does it gonna help you? I'll tell you. Okay. So if you know the entire information at a particular point, you can basically find the f of x at any other point. That is f of x plus eta d, right? F of x plus eta d. By changing the eta and d, I could basically get the f of any value. Okay, the function's value at any other point. Okay, if I know the entire local information, when I mean my entire local information at a particular point, what I'm saying is I'm talking about f of x, f dash of x, f double dash of x, f triple dash of x, and so on, everything. Okay, is this clear?
Yes.
So basically, you know the if you know the entire local information at a point, okay, you can use that information to calculate the f of x at any other point. Okay, that's what the Taylor series tells us. From this particular formula itself, we'll be able to get to know that. Okay, because to evaluate this, all you need to know is you need to know f of x, f dash of x, f double dash of x, and so on. Okay, if you know all that, you could just basically evaluate f of x plus eta d. Okay, by changing this eta d value, you could basically get I mean you could basically get the f of x at any other point. Okay, f of x plus eta d. By changing this eta d, you could basically get you could basically plot the function f also. Okay, yeah. So right now, let's say like if I taken this eta d as very small, if I taken this eta d as very small, I could basically like because eta d is very small, eta square d square by 2, it's going to be even smaller. It's kind of like, let's say you took eta d as 0.01. Okay, and then like what's going to be eta square d square, it's going to be 0.001, right? That's kind of like negligible. Okay, so if you just kind of like forget about this higher order terms, right? It's going to become, because we took this eta d as very small. Okay, what's going to become of this f of x plus eta d? It's going to be equals to f of x plus eta d f dash of x. Okay, it's going to be equal to f of x plus eta d f dash of x. Now, if you just take this f of x to the left hand side, it's going to be f of x plus eta d minus f of x equals to eta d f dash of x. Okay, so let's just look at this for a minute. So what we want is we want to minimize f of x, right? Correct. So if you want to minimize f of x, let us come to the point of this xt plus 1 equals to xt plus eta d. Okay, let's consider this as xt plus 1. Okay, this is xt plus 1 and this is xt, right? Since we want to move in the right direction, what do we want? We want f of xt plus 1 should be less than f of x, right? Correct. I mean, only then we can minimize it. Am I making sense? Okay. I'm kind of sorry because I do not have the writing pad, or else I could be showing it in a better way. So we have this f of x plus eta d, right? Minus f of x equals to this eta d f dash of x. Okay, f dash of x. How do I show it? Okay, so I'll just show it like this. Okay. This is the f of x plus eta d minus f of x equals to eta d f dash of x. Okay. Since we want this since you're moving in the right direction, we want this f of x plus eta d to be less than f of x. Okay, because that is how you know that after each iteration you are trying to minimize the value of f of x. Okay, after each iteration you're reducing the f of x value. Okay, and thereby you know that you're moving in the good direction, right? So basically this f of x plus eta d should be less than f of x, right? Am I correct?
Yes. Sir, but why are we moving in the right direction?
Oh, when I meant by right, I mean like correct direction, not the right. Correct. Okay. It's not the right left thing. It's a right. Right means correct. The correct one. Okay. Not that right. Okay. Yeah. So f of x plus eta d minus f of x. Since you want to move in the correct direction, I don't want to use right now. So since you want to move in the correct direction, we want to have this f of x plus eta d to be less than f of x, which basically means this entire value, right? It should be less than 0. Since f of x plus eta d is less than f of x plus eta d minus f of x should be less than 0, right?
Yes, sir.
Correct. Okay. So now. For us to move in the correct direction, what should be happening? Eta d f dash f x should be less than 0, right?
Yes, sir.
Okay. So we until now we can just establish that eta d f dash f x it should be less than 0. Okay. But eta right? That's a small positive constant, right? Right. It cannot be negative. The step size cannot be negative. Okay. D f dash f x only should be less than 0. Okay. D f dash f x should be less than 0. What should be the value of D such that D f dash f x should be less than 0? If you take this D as minus f dash f x, obviously D f dash f x is going to be less than 0, right? Okay.
Yes, sir.
Clear? Right. So is it clear like why we exactly took like the negative of this minus f dash f x? Okay.
Yes, sir.
Yeah. Okay. This was so that is the reason why we took this ds minus f dash of x. Okay. So and then later on, if you look at it, this for the higher dimensions. So this this f dash of x that is for a single dimension, right? Correct. So d as like minus f dash of x that is for a single dimension.
Yes.
But what about the higher dimensions? That is like when you have this when you have like more than 2 variables. That is like more than 2 parameters, like we saw for the cow case. We have the x value and the y value. That is represented as x1, x2. Okay. Basically we have 2 parameters, right? So when we have 2 parameters, then basically how we are going to update the x1, x2 value after each iteration. Instead of derivative, you take the partial derivative. Okay. Instead of derivative, you take the partial derivative. Okay, and then you update in the same way. Okay.
Great.
The same thing. xt plus 1 is going to be equals to xt minus f dash f x. Okay. Like here it won't be f dash f x. It will be gradient of f of x. Okay. Yeah, this gradient of f of x depending upon the number of parameters, it's going to give you that many partial derivatives. Okay. Dou by dou x1 that is for the first parameter, dou by dou x2 that is for the second parameter.
Right.
All right.
Yes, sir.
Okay. So move on to the next one. Okay. So this until now we have established this. Now this is just an example for it. If you take this f of x1, x2, that is the objective function. Okay, the function which we need to minimize of, that is x1 square plus 4x2 plus 8x2 square. Okay, then the gradient, right? What's going to be the gradient of it? The gradient, it should be, the first one is a partial derivative with respect to x1, which is going to be 2x1, right? 4x2 and 8x2 square, those are functions of those are x2 terms. So basically that will be that will be ignored in the partial derivatives. So it's going to be 2x1, and then that is going to be dou by dou x1. Okay, dou by dou x1 equals to 2x1, and dou by dou x2 is going to be equals to 4 plus 16x2. Right here, like as we have ignored the x2 terms, now we need to be ignoring the x1 terms when we are doing dou by dou x2. Okay, it's going to become 4 plus 16x2. Okay, you just substitute when for the for the values of 1, 3, right? For the values of 1, 3, you'll get this gradient at 1, 3. Okay, clear?
Yes.
Right. So now we have this gradient equals to 252, right? So what is going to be xt plus 1? Can someone tell me? We have this xt as 1, 3, right? And then we got this gradient f as 252. What's going to be xt plus 1? What's going to be xt plus 1? Hello? It is just subtraction. Can someone tell me? No? Okay, I'll just write it down here. I have this. I have x as 1 and 3, right? Okay, and then I have this gradient. Okay, gradient is 252, right? Now what is xt plus 1? This you could consider as x0. Okay, what is going to be x1? X1 formula, can someone tell me? It's a normal formula only. What's the formula? x0 minus eta t f dash of x, right? Right. So you can just assume eta t as 1 for now. Okay, and then you could just take it as like, since this is like higher order, higher dimensions 1, you won't be having this f dash of x, you have gradient minus of gradient, right? Correct. She will be nothing but 13 minus 252. Okay, it will be what?
Minus 1.
Yeah.
Minus 49.
Yes. So this is going to be x1. Okay. From now onwards, from now we just keep on doing the same thing again.
Sir, but why did we do eta d is equals to 1?
Like, yeah, that is just for simplification purpose. I did not tell you what exactly is eta t, right?
Yeah.
Yeah, even by definition also, even if you're going to use the gradient descent, right? If you do that 1 by t plus 1, right? Since this is x naught, this is first iteration, you'll be having that t as 0 only. Okay. Am I clear?
Yes, sir. So meaning x1 is, I'm sorry to cut you. Meaning xt plus 1 is xt plus t times of del f. Am I correct?
Can you repeat?
You are trying to say that x1 is equals to x0, like, sorry, xt plus 1 is equals to xt plus t times of del f. Is it? That's why t is equals to 0.
Not t times of minus. It's going to be minus eta t del f. Okay. Minus eta t del f. Eta t is 1 by t plus 1.
Oh, okay.
Eta t is 1 by t plus 1, right? The gradient descent algorithm.
Okay. Yes, sir.
We discussed, remember?
Yes, sir.
I'll show you. Hello, can you hear me?
Yes, sir.
Okay, so the eta t is 1 by t plus 1.
Yes, sir.
This one, gradient descent algorithm. Okay. Yeah, that one I'm talking about. Okay. Okay. So where were we? Okay, we just took this example, and then like, if you take this example, right, the cow example, that is the optimization problem is this. Objective function is this x1 minus 40 whole square plus x2 minus 40 whole square. Okay. If you do the gradient for it with respect to x1, dou f by dou x1, it's going to be equal to 2 into x1 minus 40. Dou f by dou x2 is going to be 2 into x2 minus 40. Okay. Like if you take a 0.5 comma 2, I mean this 0.5 comma 2, it doesn't have any meaning. It is just like initially they are existing, assuming this x0 as is 5 2. Okay. If you compute the gradient for phi 2, you'll be getting this minus 70 minus 76. Okay.
Yes, sir.
Minus 70 minus 76. This is the gradient del D. Okay. And then if you do this x minus of eta d del D, right? You'll get a different value. I mean, that is the minus del D is going to be equals to 70 76. Okay. Del D is minus 70 minus 76. Minus del D is going to be equal to 70 76, right?
Yes.
Okay. Yeah. So now if you just add this, that is, if you do this x minus del D, assuming again eta is 1. Okay. Eta is 1. So what you'll be getting? You'll be getting this 5 plus 70 75 plus 76 plus 2 78.
70.
Okay.
Yes, sir.
Yeah. So now the Taylor series, which are that is
Sir, your voice is breaking.
Eta d f dash plus eta d. You know, I was stopped at that part. Were you there? Hello?
Sir, your voice was really not clear. Hello, sir.
Hello. Can you hear me?
Yes.
Yeah. Can you hear me?
Yes.
I was able to hear you. Can you hear me?
Yes,
Can you
sir.
hear? Yeah. Okay. So what I was trying to say is, what we have looked at for a Taylor series is that is for a single dimension, right? Okay, that is for a single dimension. That is f of x plus eta d equals f of x plus eta d f dash f x plus eta square d square f double dash f x, right? That is just a single dimension. Okay.
Yes, sir.
That is single order. If we are talking about higher order, that is when x is a vector. When I mean by x is how does this Taylor series is going to change? It's going to be f of x plus eta d equals to f of x plus eta d transpose del f of x. Okay. Instead of f dash f x, we are going to have this del f of x. Obviously, because for the higher order, we'll be getting the gradient f of x, and then if you look, D is a vector, del f of x is a vector, but then f of x should be scalar. This is why we need to do this D transpose del f of x gradient. Is this clear? No? Am I audible first of all?
So your voice was really breaking when you were explaining this part. Fx plus nd. You were audible when you were explaining the Taylor series in one dimension, and then when you came to the higher order, your voice wasn't.
Okay. Can you hear me now? Can you hear me now?
Yes, sir. No.
Okay. So what I was trying to say is, you have this D is a vector. D is a vector in higher order.
Yes, sir.
Right? D is a vector, right? D is a vector and del f of x is a vector. Okay. But what we want is, we want this f of x plus eta d to be a scalar. X plus eta d is a vector, but then f of x plus eta d should be a scalar. Am I correct? Right. So that is why, since you want a scalar, we do this D transpose del f of x. D is a vector and del f of x is a vector, but D transpose del f of x, that's going to be a scalar. Okay. Is this clear?
Yes, sir.
Yeah. Okay. So I mean, these just you write. These just how we write it. Okay. Yes. These just for higher order Taylor series. Nothing great in that. Okay. So now what we are looked at is for this for the f of x plus eta d minus f of x, right? In terms of for the higher order, you represent it in this way, right? Eta d transpose del f of x. This is just the same as this eta d f dash of x, except for the case of this higher order. Okay, this is a more generalized form. All right, is this clear? This expression, is this clear?
Yes, sir.
Eta d transpose del f of x. I'm hearing from only one person. I hope that others are able to understand it. Okay, yeah. So what's so special about this data transpose del f of x? Okay, D is a vector, right? Del f of x is a vector, right? Correct. So what is D transpose del f of x? This is just a dot product, no? Am I correct? D transpose del f of x, it's a dot product, right? Am I audible?
Yes, sir, you are audible.
Yeah. Okay. Okay. So D transpose del f of x, that is nothing but the dot product of two vectors D and del f of x. Okay. So we want that to be less than 0. Okay. We want that to be less than 0. That is the same thing which you have seen, like f of x plus eta d minus f of x equals to eta d f dash of x. We want eta d f dash of x less than 0. Similarly, we want eta d transpose del f of x to be less than 0. Okay, because we want f of x plus eta d to be less than f of x. Okay, so what do you mean by d transpose del f of x to be less than 0? That is, what do you mean by the dot product of two vectors to be less than 0? What do you mean by that? Okay, I'll explain that here. So let's consider, like, instead of del f of x, let's assume that as w. Okay, w. Let's denote this del f of x as a vector w. Okay, w on this plane. So when will this d transpose w be equal 0? Can someone tell me? When they are perpendicular, right?
Perpendicular, right?
Yeah. So when two vectors are perpendicular, obviously the dot product is going to be 0, right? So and then w is pointing into this direction. So all the, if you could see here, all this yellow colored region, right? Yellow highlighted region. If you take any vector in that particular in the yellow color direction, right? So the dot product of d transpose, I mean the dot product of d and w, it's going to be greater than 0. Can you understand what I'm saying? Okay, so let me just try to show you this. So this is w. Okay, this is w. This is this perpendicular one. Okay, this is the perpendicular direction one, and then this is w. Okay, so if we just take this area and then this area, if you can just take like any vector in this particular direction. For example, let's say let's say I take d vector in this direction. Okay, I take d vector in this direction. Okay, I have this w here. I have this w here. What's going to be the dot product of d and w? It will be greater than 0, right? Am I correct? It's going to be greater than 0, right? Hello. Dot product of D and W, it's going to be greater than 0. Am I correct?
Yes, sir.
Right. So D transpose W, it's going to be greater than 0. Right. Similarly, if you take like any vector in this direction, it could be this, and or even like in the direction of W itself. Right. You take any vectors in this direction. The dot product of these two, right, that is D and W, it's going to be greater than 0, because the angle with which these two vectors make, right, it is less than 90. Okay, it is less than 90. Okay, so but then if you take if you take in this direction, right, that is the other side of this perpendicular line, then what's going to happen is you take any vector in these directions, the dot product of, if you take any of these vectors as D, right, then the dot product of D and W, it's going to be less than 0, because the angle with which it makes is greater than 90. These two vectors make is greater than 90. Okay, clear? Is this clear?
Yes, yes.
Yeah. Okay. So, and then what's so special about this? What is so special about this minus f dash of x is, it is exactly opposite to del f of x. Okay. I mean, if we just replace this w by del f of x, right? The del f of minus del f x, minus del f of x is exactly opposite to del f of x. It is making an angle of 180 degree. Okay, which basically means it's going to be the most negative one. Okay, among these vectors in the green color region, right? It's going to be the most negative one. Okay, because the angle with which it makes is 180 degree. Okay, clear? That is why minus del f of x gives the steepest descent. If you take this d as is minus del f of x, it's going to give you the steepest descent. Okay, clear?
Yes.
Yeah. So that is why this gradient descent algorithm is also called as this steepest descent algorithm. Okay, clear?
Yes, sir. Sir, but why
Yes.
is it so?
Meaning, why when D transpose W is negative, then it lies in the green region and so on?
Why does it lie in the green region? That's a question.
Yes, sir.
I just told you that, right? So see this is this red color line, that is a perpendicular, right?
Yes, sir.
That's a perpendicular, right? So if you take any vector, any vector in the green colored region, the angle with which this del f of x, right, it makes with these vectors is greater than 90.
Yes, sir. Is greater than 90.
It's greater than 90. So when the angle is greater than 90, then what's going to happen is the dot product of those two vectors, it's going to be less than 0. Okay.
Yes, sir. Okay. Okay, sir. I understand that.
Yeah. So, and that's the same reason why this yellow colored region, no, it's going to be d transpose w is greater than 0, because the angle with which it makes is less than 90. Okay, clear?
Yes, sir. Actually, earlier I exchanged W and D. I was taking D as the center and moving W. That's why I got confused.
Okay. I mean, but for us statistics, we're just trying to see for different D values. Okay. Yeah. So that is all we have for week 7. Okay. So yeah, if you have any other questions, you can ask. Most of you have not did the lectures. I hope after hearing this, if you try and solve it, it will be kind of like easier. I mean, at least for you to understand. Okay. The week 7, so no, it's not week 7, it's week 8. Week 8, it's going to be kind of easier when compared to the previous weeks. Okay. So if you have any questions, you can ask, or else we can close the session.
So may I ask a question from week 7?
Week 7, I'm sorry, I am not the right person to answer it because I was not the person who took the week 7. So that was taken by Mr. Vishal. Okay. So I cannot be answering your question. Okay. Yes. If you have questions on the previous weeks, you could ask them. That is the week 6. If you have any questions, you can ask. Okay. Okay then. So if you have no other questions, we can end the session. Okay. Yeah. But we have noted that point. Okay. So we'll try to arrange a session. Like at least we discuss like 1 or 2 problems from week 7. Okay. The problem solving one so that it will be easier for you. Okay. Madhuri are all right. Yeah. We'll try to arrange that. Okay. Yeah. Thanks. Okay. Thanks everyone.